Let me just share my screen with you all. Rashi, do you still have a doubt about the lead and lag part?
No, ma'am. As far as I understood that we are always talking about the forward period. Am I right?
Okay, you're basically observing the changes in the time series once a shock has been transmitted. You
Okay, ma'am.
understood that, right?
Yes, ma'am. Because I thought that how can we see the changes? I mean, the impact of shock in the backward period. Like I was confused there, but now
Okay.
I understood that we are talking about actually forward period.
Okay.
So yes, it's clear. Thank you.
Okay. Yeah, sorry about that. I accidentally closed my window. So my screen is visible to you all now, right? It's not?
No, ma'am.
Okay, sorry. Yeah, now it should be visible to you all, I think.
Yes, ma'am.
Okay. All right. So we were talking about impulse response functions, and we had discussed this particular tool of VAR models. Okay. So before I move on to the next part, let's just look at a few examples of impulse response functions, just so that you'll understand better exactly what we are talking about. So this PDF, you'll find it online very easily. I'll share it with you all. So it's been prepared by Stock and Watson, these two econometricians who you've probably come across. Watson is, I think, the same person who came up with the Durbin-Watson test. Okay, so these here are impulse response functions. So a particular shock, there has been a 1 unit change in the shock to a particular variable, okay, which means the structural error term has changed by 1 unit, and then we are seeing what is the response of a particular time series to that single shock over different periods of time. So if you look at the x-axis here, you'll see that you're looking at the effect of a single shock over 24 periods. Okay, so I'm not sure. I think this is quarterly data that has been used. Okay, so you'll find that the effect of the shock is being observed up to 24 periods. And if you look at the y-axis here, you'll see the percentage change in a particular time series. So here we are looking at inflation. So just think of inflation as the y variable, yt, unemployment as zt, and let's say interest rate is wt. Okay, just for simplicity, I'm taking this notation. Okay, so here you're seeing a shock to EYT itself. Since it says inflation shock to inflation, it means that there has been a unit change in epsilon YT, and then we are seeing the impact of that shock on inflation, okay, which is our YT variable. So you're seeing what is the percentage change in inflation itself in response to a single shock, and how inflation is responding to the shock over several time periods. Again, if you look at the second panel over here, you're seeing again a unit change in epsilon yt itself, since it's an inflation shock to unemployment. But here we are seeing the impact on the zt variable, since unemployment is a zt variable. Okay, so we are seeing what is the percentage change here uh, in unemployment as the shock is being transmitted over several time periods. Okay. Now this is our WT variable, the interest rate. So again, it's a change, 1 unit change in epsilon yt itself, and we are seeing the effect of that shock on the interest rate over several time periods. Now, if you look at this panel, here we are seeing a unit change in epsilon zt this time, since unemployment is a zt variable, and what is the effect of that on the other, uh, on unemployment itself as well as the other two variables. So I think now you'll be able to understand, since you're able to see it graphically, you'll be able to understand what an impulse response function looks like. So generally we don't deal with the numbers itself. Instead, we always refer to these graphs and then see what is the impact of a particular shock on the time series that we are considering. Okay. Now, again, one thing you'll notice is that the impact of the shock generally dies out over time. Okay. You'll find that once the shock has been transmitted, you'll find that it keeps affecting the particular time series for several periods. Okay. And then after that, you'll see that somewhere it begins to die down and the time series will converge to its long run equilibrium value. Okay. So generally, that's why all these time series are moving back towards zero. Okay. This is an exception here. You'll see that it's actually diverging. Okay. So probably there is some sort of maybe problem with the first equation here. Okay. This could be an indicator. If your IRFs are not converging once again back to zero, it might indicate that there's a problem with your estimation. So generally, they should converge back towards zero. Any doubts or questions regarding this?
Ma'am, is there any
Ma'am, you mentioned.
Yeah, can you move one at a time? Yeah. One of you, I think one person was probably Rashi. Okay. I'll let the other person go first, then Rashi can ask her question. Yeah.
ma'am, I was saying that does the shape of the graph has any meaning attached to it, like upward sloping means that latter lags have more impact or anything like that?
Uh, okay. Yeah. So let me just explain what is happening here. So if you look at the time periods itself, okay, just look at the lags and observe what I'm saying. Now the instantaneous impact, or in the same time period, once there's a unit change in epsilon yt, okay, so if there's a shock to that first equation, the structural error term from the first equation, once there's a shock in the same time period, you will find that inflation is increasing by 1%. Okay, so at time period 0, when t is equal to 0, you'll find that inflation has increased by 1%. Then after that, probably in the first time period, because of the autoregressive nature of the whole series, since you're dealing with the var model, in your equation you'll have yt is equal to a1 naught plus a11 yt minus 1 plus a1 uh, 2 zt minus 1 and so on. Okay, so because of the autoregressive term which is present on the right hand side, in the next period, your epsilon yt plus 1 is going to go back to 0. Okay? There will no longer be a shock. The shock is happening only at one particular point of time. Okay? In the next period, there is no shock. But the effect of that single shock is being felt throughout time through your yt minus 1. Okay? And the other lagged variables. So you'll find that the effect of that shock remains, and that's what you're seeing. So then if you take the first lag here, okay, just think that it's somewhere here. So after that, at time period, if you're looking at yt plus 1, okay, then at time period t plus 1, you'll find that What is the percentage change in yt plus 1? It might be 0.8 or something like that. Okay. Then in the fourth time period, if you're looking at it, okay, let's try and see, it's probably 0.6. Okay, so that is the impact of the shocks. So your yt plus 4 value, it would have changed by 0.4 because of this single shock. Okay. Are you able to understand now?
Yes, ma'am.
Okay. Yeah. What about Rashi? What was your question?
Yes, ma'am. I was also asking the same thing. Thank you.
Okay. So basically, you're looking at how this shock is going to affect YT in different time periods, and that's how you'll interpret the graph also. Again, in addition to that, you'll notice that there are these dotted lines. Okay, so I just want you to guess what they are. You've seen them many times before now. What are they?
Are they depicting confidence interval?
Yes. Okay, so they are the confidence intervals. Now, the reason that we have these confidence intervals is because your parameters in the VAR model itself, once you estimate the VAR model in the standard form, the estimates that you get are probably going to have some margin of error, right? Okay, you might not be able to estimate those coefficients very precisely. So because of this, since your coefficients are not estimated precisely, when you're looking at the IRFs or trying to find out what are the impulse response functions, again, these estimates could be generated with an error. Okay, so these could also be subject to an error. So that's why we create these confidence intervals. We are not really going to discuss how we do it, but these confidence intervals are basically telling us that the true value of the impulse response function will lie somewhere in this band. Okay, for example, if it's a 90% confidence interval, the true value of the impulse response will lie somewhere within this interval. Okay, so if I construct 100 such intervals, in 90 of them, the true value will actually lie within this band, if it's a 90% confidence interval. If it's a 95% confidence interval, then if I construct 100 such intervals, then in 95 of them out of 100, the true value will lie within this band. That's what the confidence interval itself means. So we'll come back to this PDF. Let me just move on to the next part. Let me know if you have any doubts or questions at any point of time.
Ma'am, this IRF, what you mentioned,
Yes.
is this an average over the data or
No,
of all the lags?
no, it will not be an average. I'm not sure what you mean by average.
By that I mean, over the data, whatever data is taken,
Hmm.
right? There are lags are continuously there, right? So the shocks are
Yes.
continuously there. So
Or
when you draw a function like this is for a single shock you have mentioned.
yes.
So, I mean, is it possible to delineate each shock like this, or you average this out over various shocks over the data, given data?
Mm, okay, I'm not sure that I understand the question very well, but uh, what I can tell you is that whenever we are discussing the IRF, for example, in this first panel, it's a shock to epsilon yt, for example. Here it's a shock to epsilon zt. Here it will be a shock to epsilon wt. So it's a single shock, and then we are seeing the impact of that shock on a particular time series. Here in this, if you look vertically, it's on inflation. Here it's on unemployment. Here it's on the interest rate. We are not averaging out anything. We're just seeing what happens, how the time series behaves in response to the shock, and what will be the change in the time series in response to a single shock. That's the only thing that we're looking at.
So the impulse response function, what I'm saying, is specific to each shock.
Yes. So here, if you look at this horizontally, here you're looking at the impulse responses if there's a shock to epsilon yt. So the structural error term from your first equation, if there's a shock to that, then what is the impact on all the other variables in your VAR system? That's what you're looking at. Then in the second one, if you look horizontally, again, if there's a single shock to epsilon zt this time, Okay, what is the impact of that on all the other time series which are there in the system and on that particular variable itself. So since each equation will have a particular structural error term, we are basically giving a shock to each of those structural error terms, and then in each of these panels, we are seeing what is the impact of that shock. And then we are saying that since all our variables are stationary variables, we expect that these IRFs are going to converge to zero. So the impact of the shock will not be felt endlessly or forever. It is going to die out. It will be a temporary shock. The effect might last for up to 24 periods in this case. Okay, but it is going to die out after a certain period of time. Is that all right?
Ma'am?
Yes.
Ma'am, in line with what just asked, so we are trying to say that there was only one shock in one particular time period, or the impact that we are trying to see is isolated of other shocks. Like if we are talking about the unemployment, then the magnitude change is only due to the inflation shock, not because of any other shock.
Yes. Yeah. So you're isolating each shock. You're not allowing the shocks to what do you say? Impact each other. And also because in your VAR model, you are going to impose certain restrictions to allow for identification. So because of this, you will make sure that your structural error terms are no longer correlated in some sense. So when you're looking at here, for example, the inflation shock, here you'll be looking at the impact of that shock on these variables without it affecting the other shocks. Okay, so we are trying to make sure that the other shocks are not affected. What I can do is in your set of notes, I'll include a couple of equations so that you'll be able to see how exactly that shock is being transmitted. Wait, let me see if I can do that in these notes itself. Okay, yeah. So I want you to look at this part here. Okay. So if you're looking at this, since we are getting the impulse response function from the VAR model in the standard form, okay, so what we are dealing with is actually these terms. These are the residuals from your regression. Now, what we are doing in the impulse response function is, for example, if there's a unit change, the shock is to epsilon yt. Now, it's only going to affect the first equation here. Okay, so it's going to be transmitted to yt itself. Since this PDF is for some other, it's for a particular data set. Okay, so don't keep this in mind when I'm discussing this part. Okay, so here, since the shock is to epsilon yt, it will affect yt, which is our first equation. Let's see if it's there. Yeah. Okay, but it's not going to affect zt. All right. Now, if you look at this part now, if there's a shock to epsilon zt, you'll see its impact on yt as well as zt. Okay. So now let me try and explain it a little more in detail. So let's say there's a 1 unit change in epsilon yt here. Okay, so that is going to affect yt, and you might see that yt changes instantaneously. In the same time period, let's say that yt, the value of yt increases by 1%. Okay, same, I'm using the same reference that we just saw. Okay, then in the next period, for example, epsilon yt plus 1, it is going to go back to 0 since the shock was only at time t. Okay, so epsilon yt plus 1 will go back to 0, but we'll keep seeing the impact of this on yt plus 1, yt plus 2, and so on. Okay, so that is what we are tracing in the impulse response function. Now, when this is happening, for example, for yt plus 1, how is it affecting? Since it would have affected over here, okay, you'll find that the impact of the shock will be carried forward through this lag term here of yt. So it will still affect yt plus 1, yt plus 2, and so on through these autoregressive terms. Okay? So let's say that in the next time period, yt plus 1, the value of yt now changes by maybe 0.4%. Okay, so it will gradually keep diminishing. Sometimes it could increase and then decrease. Okay, sometimes it will just keep decreasing. So this is how you will trace the impact of a single shock. So this epsilon yt shock, it's going to affect only yt. Now, if you look at epsilon zt, okay, since it's appearing or going to affect both the equations through these regression residuals, you'll find that if there's a unit change in epsilon zt, it's going to affect yt as well as zt. Okay, so the impact of this shock will be felt on yt as well as zt. But for example, here, since epsilon yt does not appear in this zt equation at all. Okay, so if there's a 1 unit change to epsilon yt, it's not going to affect zt at all, and the instantaneous impact of epsilon yt on zt will be 0. Okay, so it's not going to affect, or there's going to be no change in zt instantaneously. Later on, it might affect through this lag term. Okay, but the instantaneous impact itself will be 0. I don't know if I've confused you more or I've made it clearer to you all.
Ma'am, from the with the help of those graphs that you show, could you just show once again, please? So, ma'am, the interest rate is the ZT.
Yeah.
Okay, thank you, ma'am.
Interest rate is not ZT, WT. I said inflation is YT, unemployment is ZT. I'm making interest rate WT.
Okay. Yes.
So for example, here you'll see that if you look at this part here, let's see this, since it's clearly, or okay, let's take this one. It's very clear over here. The unemployment shock to inflation. Okay, so here it's probably the case that you've imposed a restriction in such a way that epsilon ZT shock, it's not going to affect inflation instantaneously. That's why if you look at the instantaneous impact, it's actually 0. There's no effect on inflation if there's an epsilon ZT shock, okay, instantaneously. Then in the next few time periods, you begin to see the impact. Now, how is it being transmitted over here? Through the lag terms. Okay, I hope it's a little clearer at least now.
Yes, ma'am. Now it's
okay.
better.
Here also you can see, again here you would have imposed some sort of a restriction, because of which if there's an epsilon here WT, okay, since interest rate is my WT variable, so if there's a unit change in epsilon WT, it's not going to affect inflation again instantaneously because I've imposed some sort of a restriction. So there's no instantaneous impact. The effect is 0 instantaneously in the same time period. But after that, it begins to affect inflation through the lag terms, which is your YT minus 1, ZT minus 1. It's going to affect through that channel. Okay. Later, I'll show you what the restrictions are after we discuss the next tool. So we'll come back to that in a moment. Okay. Yeah.
Ma'am, can you share this paper?
Yes, I will be sharing it. You want me to share it right now, is it?
No, no, ma'am. Whenever you have time.
Okay, yeah. Yeah, so let's move on to the next part. So we said that the impact of these impulse response functions, it's going to be finite. They're going to die out over time, and the impulse response functions itself will converge back to the long run equilibrium value. Okay. Yeah, so I think this is the point that I was trying to make. So since you're using this Cholesky decomposition, okay, so you're basically imposing certain restrictions on your model so that you can decompose the errors itself in your model in a certain way. Okay, So you're seeing that because of the restriction we imposed, it was B21 equals 0. Okay, that was the restriction that we had imposed yesterday. So because of that, you will find that E1T, okay, which is your regression residual, it is made up of both the structural error terms. Whereas this second regression residual, E2T, okay, it is going to reflect only the pure structural shocks that we are going to see, or it's going to reflect whatever is happening to the structural error term directly. Okay? So the decomposition basically forces an important asymmetry on the system, since an epsilon zt shock has a contemporaneous effect on both yt and zt. Okay? But it does not have uh, but an epsilon yt shock will not have a contemporaneous effect on zt. Okay, so that is the difference here because of the kind of decomposition that we've used. So due to this, you'll find that 19 and 20 are known as an ordering of the variables. Okay, so you're basically imposing a certain structure or order on your system of equations so that you will actually be able to recover the structural estimates. Okay, and this sort of a decomposition is known as a Cholesky decomposition, and this will be called an ordering of the variables. Okay, remember that this refers to the triangular portion of your B matrix. Okay, since the lower part, the lower triangular portion will have a series of zeros. So that is the kind of decomposition that you're using. Now an epsilon zt shock directly affects E1t and E2t, but an epsilon yt shock does not affect E2t. Okay? So this is what I just mentioned. Okay? Hence zt is said to be causally prior to yt. Okay? So you'll find that even if you look at the equations itself, let's see. Okay, just try and remember the equations. It'll take me some time to find them here. Okay? But if you look at the equations, you will find that since zt is not affected by the contemporaneous value of yt, okay, because of that, that zt in some sense becomes exogenous. Okay, zt is not determined by yt, instead it's only determined by the lagged values of yt, whereas yt is affected by the current value of zt. Okay, so yt will be an endogenous variable, but in some sense zt becomes an exogenous variable since it's not affected by yt. Okay? It's only affected by its lags. So because of this, zt is said to be causally prior to yt, and once you know zt, it will be easy for you to determine what is yt, what is the value of yt. Now, as the IRFs are constructed using the estimated coefficients and each coefficient is estimated imprecisely, the IRFs will also contain some errors. Okay? Because of this, some confidence intervals are usually constructed around these IRFs to allow for parameter uncertainty that is always part of the estimation process. This is what I had mentioned earlier also. Any doubts or questions so far related to IRFs or VAR models? So the next set of tools is called a variance decomposition. So what we do here is, since a VAR model is used for forecasting purposes, once we generate the forecast, we try and determine what portion of the forecast error variance is explained by a particular variable that is there in the VAR system. Okay? So let's look at this in greater detail. So first we'll discuss the forecasting part and then we'll move on to the forecasting errors and their variance. So to understanding the properties of the forecast error is very useful in unraveling the interrelationships among the variables in the system. Since the primary focus in a VAR model is to understand how different variables are related to each other, how they actually affect each other, you'll find that once we get the forecast error, we usually break it up and see how much of the forecast error variance is due to a particular variable. Okay? Now, if we know the coefficients of A naught, So A naught is basically our vector of intercept terms or constant terms, and A1 will be all the coefficients associated with the lagged values of the variables. So if we know all these coefficients and then we want to forecast the various values of xt plus I conditional on the observed value of xt, we can go about it in this way. Okay. So this part might not be visible to you, so I'll just read it out. Let me know if you want me to zoom in further, okay? So updating equation 11 by one period. Okay, so equation 11 was basically the equation for the whole VAR model. So xt plus 1. So xt is our vector of endogenous variables. So it will have yt, zt, whatever other endogenous variables are there in our model. So xt plus 1 is equal to a naught plus a1 xt plus et plus 1. So this is how we'll generate the one step ahead forecast. Okay. Okay, so if you take the expectation of xt plus 1, we obtain this. Okay, so the one step ahead forecast error will be this term here. Okay, so similarly, you can forecast 2 periods ahead and so on. Okay, so this will give you the 2 step ahead forecast. Okay. Okay. So taking conditional expectations, the 2 step ahead forecast of xt plus 2 is this, the expected value of xt plus 2 based on information available at time t. Okay. So the 2 step ahead forecast error will be this. Okay, so if you keep repeating this process n steps ahead or n periods ahead, and if you forecast all these time series that you have in your WARE model n periods ahead, then you'll be able to generate the n step ahead forecast. Okay? So this is the form that the forecast will take, and your n step ahead forecast error will be this. Okay? So if you do xt plus n minus expectation of xt plus n, you'll get these terms. So we can also consider the forecast errors in terms of equation 18, okay, which is the VMA from our structural model. So VMA is basically the vector moving average representation that we were using yesterday. Okay? So again, using that, remember that you're just basically iterating the whole time series in such a way that you will be able to get it in the form of some mean value and then the moving average error terms. I'll send you that set of notes by tonight, all right, so that you all can see how exactly we are getting the VMA representation. So here this n step ahead forecast can be written in this form. Okay? And the one step ahead forecast error will be of this form. Okay? So the n step ahead forecast error will be xt plus n minus expectation of xt plus n. And we'll see what exactly the term is that is produced in the next page.
Ma'am,
Yes.
ma'am, I got disconnected when we shifted the standard VR model one time period. So I had two questions.
Hmm.
Ma'am, first, for forecasting, if we get or if we already get the AI matrices, then why do we need to decompose the variance? Because we can still forecast the xt vector if we have the AI matrices, right?
Yeah. So you will have to be a little patient and see why exactly we are decomposing the forecast error variance. Okay, so once I finish this portion, you'll be able to understand it.
Okay, ma'am. And another question, for the A naught matrix, the
Yeah.
diagonal elements will all be zero, right?
A naught is basically a vector. Yeah. So
A
it'll
naught is
just,
a n by n vector, right?
no, it'll be an n into 1 vector. Since you have n equations, suppose you have n variables in your var model, you'll have n equations. Each of those n equations will have a single intercept term, right?
Okay, ma'am. Okay.
Your other matrix, A1, will be an n by n matrix.
Okay, okay, ma'am. Got it. Sorry.
No, it's fine. So here, this will be the n step ahead forecast error, okay, which is generated. So again, it's basically, you can see a cumulative sum of all the error terms. Okay? Since we are dealing with the structural model or the model in the structural primitive form itself, you're getting the structural error terms here. So now if you take up only the YT time series, okay, if you take up the YT sequence, then the n step ahead forecast error for YT will be this. Okay. Probably once I send you the notes, you'll understand exactly where these terms are coming from. Some of you might be able to follow already, but for the rest, you'll be able to understand a little later how exactly these terms are coming in. Okay? So these are basically your coefficients from the phi I matrix, which had our impulse response coefficients basically. Okay. So denote, if you want to denote the n step ahead forecast error variance of yt plus n as sigma yn square. Okay. So then we can just take expectations here, okay, and find out what is the forecast error variance. So you'll get this term in brackets and you'll have sigma square y here outside the brackets. Okay. Similarly, also because in the yt equation you have zt, the lags of zt also appearing, you'll also have these terms associated with the zt variable. Okay. So your forecast error variance, now you can decompose it and find out how much of the error variance is because of the y variable, how much of the error variance is because of the z variable. Okay. Now, as all values of phi jk I square are necessarily non-negative, okay, since you're squaring all these terms, they are going to be non-negative. So you'll find that the variance of the forecast error increases as the forecast horizon n increases. Okay. Since all these terms are squared and they are non-negative, you'll find that the variance of the forecast error, if you're forecasting n periods ahead for yt, okay, then the variance of the forecast error will keep increasing as the time horizon increases. Now it is possible to decompose the n step ahead forecast error variance into the proportions due to each shock. Okay. So the proportion of sigma yn square, the n step ahead forecast variance basically, due to shocks in the EYT and EZT sequences are respectively given by these formulas. Okay. So what you need to do is take the n step ahead forecast error variance, okay, divide this first portion. Okay, this first portion is clearly because of the EYT shock. Okay, shocks to the EYT structural error term, sorry, epsilon YT. So take that portion of your forecast error variance and divide it by the entire forecast error variance. Okay, so you'll get the proportion of the forecast error variance due to shocks in epsilon YT. Now do the same thing here. Take the portion that is related to epsilon ZT alone, okay, and divide that by the entire forecast error variance, which has been calculated n steps ahead. Then you'll get the proportion of the forecast error variance due to shocks to epsilon ZT. Okay. So how does a particular shock, how does it contribute to the forecast error variance several periods ahead? That is what you are finding out. okay, through this sort of decomposition of the forecast error variance. Any doubts or questions? Any doubts or questions here?
No, ma'am.
Okay. So most of the time, what you will find is, let me just go back to this. I think we're almost, yeah. So before I explain for a particular variable, the forecast error variance decomposition will tell us the proportion of the movement in a sequence. So how much of the movement in a particular time series basically is due to its own shocks versus shocks to the other variable. Okay? So most of the time what you will find is, for most of the variables, for most time series variables or macroeconomic variables, you'll find that most of their forecast error variance is explained by their own shocks. Okay? So for example, if I take YT and decompose its forecast error variance one step ahead, n steps ahead, okay, how many ever steps ahead, then I'll find that most of the movement in YT is because of its own shocks, which means that shocks to epsilon YT are generating most of the uh, forecast error variance or most of the movements in YT itself. Okay, whereas shocks to epsilon ZT will probably explain very few of the movements in a particular time series. For example, in our case, in YT. Okay? Whereas if I take up ZT and forecast it n steps ahead and then find the forecast error and its variance, then I'll find that in the case of ZT, epsilon ZT will explain most of the movements in ZT, or will explain a larger proportion of the forecast error variance. So shocks to epsilon ZT will explain most of the forecast error variance of ZT several periods ahead. Okay, whereas shocks to epsilon YT will not explain much of the variance of the forecast error variance for ZT. Okay. Now the reason for this is, if you look at the structure of our VAR model itself, the way we've constructed it is in that fashion. Okay, that most of the forecast error variance is likely to be explained only by lagged values of YT and ZT rather than the contemporaneous values of YT and ZT. So because of this reason, you'll find that most of the forecast error variance is explained by shocks to its own variable, okay, compared to shocks to the other variable. So for example, YT will be affected mostly by epsilon YT shocks and very less by epsilon ZT shocks, because of the fact that ZT is going to enter in a lagged fashion in the YT equation, although it also enters contemporaneously. Because of the structure of our VAR model, you'll find that its own shocks explain most of the forecast error variance, okay, for both the variables or for most variables in most VAR models. I'll go back to that PDF so that you can actually understand using certain numbers. Okay. Now, impulse response analysis and variance decomposition together are called innovation accounting, and they're very useful tools to examine the relationship among economic variables. So you'll find that most of the time we do not really discuss the estimates of the coefficients. We straight away move to impulse response functions and variance decomposition to understand the movements in a particular time series and how that particular time series is evolving over time. Okay. So I'll just come back to that PDF. So I'll just go through certain important portions of this, okay, because it will help you in your understanding. So 2 decades ago, so this was somewhere in 2000s, this PDF I think was written. So Christopher Sims 1980 provided a new macroeconometric framework that held great promise, which is VAR models. Okay, so he contributed hugely to the development of VAR models, as I mentioned yesterday. Okay? And compared to what we studied earlier, ARIMA models, which have simply a single equation and you're looking at a single variable and how it evolves over time. Here, a VAR model is an n equation, n variable linear model. Okay, so this part is very important. It's a linear model. We are studying only linear VAR models so far. Okay, in which each variable is in turn explained by its own lagged values plus current and past values of the remaining n minus 1 variables. Okay. So this is where the feedback portion comes in. If you have current values of the remaining n minus 1 variables, then there will be feedback between the two variables. Okay. So all of the equations will have this similar structure, that each variable is explained by its own lags as well as lags of the other variables in the system. And you could also have current values of the other variables in the system. And this helps us to capture the rich dynamics that are there in multiple time series. Then if you look at this, they talk about the identification problem again. And here, let's see what is the particular model that they have used. Okay. So in the next two sections, we take a quantitative look at these and related questions using several 3-variable VARs estimated using quarterly US data. Okay, so they are using quarterly US data on the rate of price inflation. Okay, that is this variable pi t, the unemployment rate UT, and the interest rate RT. Okay, and they've used the federal funds rate for RT. And this is the time period that they've used for analysis using quarterly data. Okay, then VARs come in different varieties. You have reduced form, recursive, and structural VARs. So structural VAR is basically a primitive system. Okay, then reduced form VAR is what I was mentioning earlier. Each variable will be expressed as a linear function of its own past values and the past values of all other variables being considered, and a serially uncorrelated error term. So this is the VAR model in its standard form where you don't have any restrictions. Okay, so that is your reduced form VAR model. Then if you have a recursive VAR model, that is where you're imposing certain restrictions on the coefficients of the contemporaneous variables here. Okay, since our VAR involves 3 equations, the current unemployment as a function of past values of unemployment, inflation, and the interest rate, then inflation as a function of past values of inflation, unemployment, and the interest rate, and similarly for the interest rate equation. Now each equation is estimated by OLS since the right hand side variables are identical. Okay. Then the number of lagged values are to include in each equation can be determined by a number of different methods. I'll come back to that and discuss it later. Okay. Here they are using 4 lags in their example. Okay. Now for their recursive VAR itself, okay, they have considered a 3-variable VAR ordered as this. Okay. So inflation forms the first equation. This is the dependent variable in the first equation. Then you have the unemployment rate. Then the interest rate being the dependent variable in the third equation. Okay. So that's what they've said. So for the first equation, the regressors are lagged values of all the 3 variables. Okay. Now, because of this, if you look at the structure, okay, I'll come back to this in a minute. Now, in the second equation, the unemployment rate is the dependent variable, and the regressors are the lags of all 3 variables plus the current value of the inflation rate. Okay, so here a particular restriction has been imposed that the current value of the interest rate will not affect unemployment. Okay, that is the restriction which has been imposed. Again, if you look at the first equation, the restriction is that the current value of unemployment as well as the interest rate will not affect inflation. Okay, so these are the restrictions which have been imposed. Now the interest rate is the dependent variable in the third equation, and the regressors are the lags of all 3 variables, the current value of the inflation rate plus the current value of the unemployment rate. Okay, so here for the interest rate variable, you will find that it is affected by the contemporaneous value of both inflation as well as unemployment. Okay, so the structure here or the kind of restrictions that have been imposed are slightly different from what we saw. This is likely to be an upper triangular matrix. Okay, instead of a lower triangular matrix where the lower triangle has zeros, here the upper triangle is probably going to have zeros here. Okay. Again, they're going to estimate the equation using OLS. Okay. Then I won't go through this entire thing. I'll send it to you all so that you all can read it leisurely. Now, the part that I'm interested in, since I've already showed you the IRFs, we'll go straight to the variance decomposition. Okay. Okay, that comes right at the end, I think. Right, so this is the variance decomposition part from the recursive VAR model, which has been ordered this way. Okay, so if you look at the variance decomposition of pi, so here we are forecasting inflation several periods ahead and then seeing what portion of the forecast error variance is explained by its own shocks or by shocks to unemployment or by shocks to the interest rate. Okay, so here you'll see that if you're forecasting only 1 quarter ahead, then 100% of the forecast error variance is explained by shocks to epsilon yt, okay, or shocks to the inflation error term. Okay. Then if you forecast 4 quarters ahead, 88% of the forecast error variance is explained by shocks to the inflation variable itself. Okay. Then if you forecast 8 quarters ahead, 82% of the forecast error variance is explained by shocks to the inflation variable again. Okay, 12 quarters ahead also you see the same result. Now, if you want to what do you say, interpret these, can anyone try and interpret for R? Let's see if you can interpret for R. Does anyone want to try?
Ma'am, for R, can we say that in the first time period or the first interval that we are taking, it has no impact?
Yeah.
I'm
Okay.
sorry.
No, that's
and
correct.
if it is 2 throughout, so it is going constant or it has remained there, like the impact is.
Okay. Okay, I think one thing is you're still thinking in terms of the IRFs, so you're explaining it like how you would explain the IRFs. So here, how you'll explain it is if there's a shock to the inflation error term. Okay, so I'm denoting, let's say, epsilon pi t. Okay, so that now that you're familiar with this notation, let me just use epsilon pi t here. Okay, so if there's a shock to epsilon pi t, then 0% of the forecast error variance of inflation in the first quarter, if I'm forecasting 1 quarter ahead, then 0% of the forecast error variance is explained by uh, shocks to epsilon RT here. Okay. Then,
Ma'am.
yeah.
So, ma'am, basically, that's why we are decomposing the variance in a sense to verify our restrictions. Because in the
Yeah.
first restriction, the contemporaneous effect of unemployment and interest rate was set to be zero. And the
Yeah.
second restriction, the impact, basically the impact of unemployment and the interest rate was set to be zero on unemployment.
Yes.
So that's why we decompose the error variance.
Yeah. Basically, whatever restrictions you impose, you'll see that getting reflected in the IRFs as well as the variance decomposition. So
So,
here,
ma'am, then will it not be kind of like the opposite of the scientific method, like cherry picking the evidence to suit the hypothesis rather than changing the hypothesis to suit the evidence. Like what I mean is, VAR models can only be used when such restrictions hold true. If those restrictions don't hold true, then we can't use VAR models.
No, generally, when you're imposing the restrictions, you will have to do it based on some theory. Okay, generally, VAR models are said to be atheoretical, but when you're imposing the restriction, if you believe for a particular reason, for example, that YT does not affect ZT contemporaneously, it affects ZT only with a lag, then you will impose that restriction that beta 21 is equal to 0.
Yes, so
For
matlab,
example,
the restriction should be backed by theory, right? You
yeah,
can't just summon them
theory,
out of thin air if they aren't.
yeah, yes, it has to be backed by theory, or even if you don't have a particular theory, based on your observation of the real world, that's where our theories also come from generally. So based on your observation, you will impose those restrictions.
Okay. But if our observations don't support the restrictions, then we can't really use the VAR model, can we?
Let's say you might not be able to estimate the VAR model in the recursive fashion. So you will have to do something else. For example, instead of using this recursive method, there are other sort of decompositions, okay, which we are not discussing. It'll take a lot of time and it's very advanced. So there are structural VAR models where instead of having this sort of a triangular format of restrictions, instead you will again impose based on theory. It's there in this PDF, so those who are interested can read those portions. So again, based on theory, you will have a certain set of restrictions, but they will not assume a triangular form in your matrix. Okay. So,
Okay.
but again, you will be restricting certain coefficients to equal 0 so that you can achieve identification. Or there's also something known as the Blanchard core decomposition. Again, we won't be discussing that. So that has a different method of imposing restrictions and so on.
Okay.
There are other
Thank you.
ways to do the same VAR estimation without using this recursive form of imposing restrictions. Okay, but since this is simply an introductory course, we won't be dealing with that right now. But it's all there in the PDF. So if you're interested, you can read it.
Ma'am, can you also share those PDFs that you showed us during the Chow test and the before that during the unit root tests?
Yeah,
The
yes, I
paper.
will. Okay. And I might not be able to do it immediately because I don't have access to it right now, but I'd like to send you all the some of the original papers at least. So I'll try and send that to you all. It might happen at the end of your entire semester, okay? So it won't help you with your exams, but I'll still send it across to you later. So let me just quickly discuss this part and then we'll break for 5 minutes. So here what I'm saying is, so 100% of the forecast error variance of inflation, if I'm forecasting inflation 1 quarter ahead, will be explained by its own shocks, whereas 0% of the forecast error variance will be explained by shocks to the interest rate term. Okay? And 0% of the forecast error variance will be explained by shocks to the unemployment error term. Okay? Similarly, if I move down and I forecast inflation again 8 quarters ahead, okay, this time 16% of the forecast error variance will be explained by shocks to the unemployment error term. Okay, epsilon unemployment. Okay, just think of it that way. And similarly, 2% of the forecast error variance, if I'm forecasting inflation 8 quarters ahead, will be explained by shocks to the interest rate term. Okay, so this is how I'll interpret my results. Then again, if I come to this, okay, if I look at this, here what I'm doing is forecasting the interest rate several quarters ahead. So when I'm forecasting the interest rate 1 quarter ahead, 79% of its forecast error variance is explained by its own shocks. Okay, whereas only 19% is explained by shocks to the unemployment error term, and only 2% is explained by shocks to the inflation error term. Then if I forecast the interest rate 12 quarters ahead, then 25% of the forecast error variance of the interest rate is explained by its own shocks, okay, 12 quarters ahead. Then 57% of the forecast error variance is explained by shocks to the unemployment error term, and 18% is explained by shocks to the inflation error term. Okay? I hope this is clearer to you all now. So you'll find that if I'm forecasting for short periods, okay, so most of the forecast error variance will be explained by shocks to the own variable or shocks to its own variable, whereas very less will be explained by shocks to the remaining variables in the VAR model. Whereas when I increase my forecasting horizon and I forecast several quarters ahead, more of the forecast error variance will be explained by the other variables compared to shocks to the own variable. Okay, I hope it's clear to you all now. Any doubts or questions?
Ma'am, is this true for all types of VAR models or only this particular form of the VAR model?
No, this is generally true for all VAR models. That for more recent periods, you'll find that most of its forecast error variance is explained by its own shocks and very less by the other variables. But at longer horizons, more of the forecast error variance will be explained by the other variables. This is a general thing that we notice for all models.
Yeah, for instance, in this table which you have just shown, B first table, B1,
Yes. Okay.
the interest rate, for example, is shown as having no impact on the inflation, and this is over a 40-year time zone of US, right? 1960 to 2000.
Hmm.
Now that's very surprising because the entire 80s were in that high inflation zone of US and high
Yes.
interest rates, and the entire underlying theme of monetary policy comes to a question with this kind of
Yes,
analysis.
that's a good observation actually. So this may be because of what was noticed later. I'll be mentioning it in the second half of the class. So when I mention that part, we'll see why exactly something like this might have happened.
Okay.
Okay, so if there are no other doubts or questions, let's just break for 5 minutes. I know this part might have been slightly confusing for you all, so I'll share the PDF and the other notes by tonight with you all, okay, so that you all can go through it leisurely and try and understand it. Okay, so let's break for 5 minutes. We'll meet at 3:43. Okay. Okay, I hope all of you are back. Okay, so this is where we had stopped. So IRFs and variance decompositions are the two main tools that we use whenever we're discussing Bayer models. Then other things to keep in mind while estimating Bayer models are how do we select the lag length. Okay? So just like how we did for ARIMA models, there we were using AIC and SPC to actually select the lag length, but to select the best fitting model. Okay, the same way here, when you're selecting the lags, you'll basically be seeing uh, how many lags yields or produces a best fitting model for you. Okay, or how many lags is it optimal to include whenever you're estimating your VAR model. So similarly, here also we use the AIC and SBC criteria to actually select the best fitting VAR model and choose the lag length. So here, if you look at the AIC, here we'll be using the multivariate generalization of the AIC and SPC. For ARIMA models, we were using the univariate form of these criteria. Okay. So here in a VAR, since there are n variables, so we'll be using the multivariate form of these AIC and SPC criteria. Okay. So here, this sigma here is basically your variance covariance matrix of the residuals. Okay, and this indicates that it's the determinant of the variance covariance matrix of the residuals. Then n is the total number of parameters estimated in all the equations. T will be your sample size or the number of usable observations. Once you've taken differences and lags, how many observations are you actually using to estimate your VAR model? That will be your T. Okay. So n will be the total number of parameters estimated in all the equations. Can anyone recall and tell me how many parameters there will be in an n variable VAR model? Does anyone remember? Am I audible to you all? At least you can try and guess even if you don't remember.
Ma'am, I'm sorry, I lost you for some time. Could you please ask? What was the question?
Yeah, I'm asking in an n variable VAR model, how many parameters will be there in the VAR model? What are the total number of parameters in the VAR model?
Was it something like n square plus pn?
You're close.
Something like that, ma'am. I'm forgetting because n square will be uh, the parameters we need to estimate for the n variables, and then the other parameters, I forgot the coefficient of that.
Okay. If you remember the structure, basically you will have n intercept terms. Okay. Then you will have your A1, which is an n by n matrix, and there could be p lags of those variables which are there in your VAR model. Okay. So because of this, you'll have n plus pn square. So that is the total number of parameters in your VAR model. Your n intercept terms, then the lagged variables will all have coefficients which will be captured in an n by n matrix, and since if you're including p lags, there'll be p such terms. Okay, so it will be n plus pn square. That will be the total number of parameters in the VAR model, in an n variable VAR model. Okay?
Yes, ma'am, that's what I meant. I
Yeah.
said the opposite.
Okay, so here if you'll notice, okay, similar to what we had learned while learning ARIMA models, you'll find that the AIC, okay, it's made up of these two components. So whenever you add too many lags of a particular variable, if you're increasing the number of lagged values, then what will happen is it's very likely, since you've added more regressors or explanatory variables, that your residual sum of squares is going to decrease, or this term, basically your ln determinant of the variance covariance matrix, this particular term is going to reduce in value. Okay. But at the same time, since you're adding more explanatory variables, you'll be adding more parameters for estimation. So this term n is going to increase. Okay, so there's always going to be a trade-off. As you add more and more lags, this term might reduce, but this term will be increasing. Okay, so here also, when we are selecting the number of lags or the lag length for your VAR model, you'll have to balance this trade-off and choose the model which has the lowest AIC or SBC value. Okay, so your criteria will be again minimization of the AIC or SBC value. Okay, when you're selecting the lag length. So suppose if you have quarterly data and you want, if you're trying to choose between 4 lags, having 4 lags of all the variables or 8 lags of all the variables, you could estimate the model for both these specifications. Okay, one which has 4 lagged values of all the variables, the other has 8 lagged values. Then check what is the AIC value for these two models, for the 4 lagged values model and for the 8 lagged values model. Whichever gives you a lower AIC value, that will give you the best fitting model. Okay, so suppose 4 lags has a lower AIC value compared to 8 lags, then you will select 4 lags for your VAR model and go ahead with that estimation and the rest of the generating IRFs, variance decomposition, and so on. So you'll use that model for your analysis. Okay, any doubts or questions regarding this? This is fairly straightforward, so I don't think. Okay, so next we move on to another very important test or tool which is often used with VAR models. Okay, so this is actually a separate test, but it's once you estimate VAR models, generally the next process which or procedure which is involved is to actually check for causal relationships between the variables, okay, that are there in your VAR model. So this is basically known as a grandeur causality test. So what we want to do here is to test whether the lags of one variable enter into the equation for another variable. Okay, so when we are doing this, we want to see whether lagged values of, for example, yt, whether it can help us better predict the future values of zt. Okay, only then will we actually want to include the lagged values of yt in the zt equation. So for example, in a 2 equation model with t lags, yt does not grandeur cause zt if and only if all of the coefficients of a21L are equal to 0. Okay, so here if you take all the coefficients which are associated with the lagged values of yt, okay, and look at the zt equations. So if you estimate your VAR model and you find that all your coefficients are insignificant, so basically they are statistically equal to 0, or they are not significantly different from 0. So because of this, you can conclude that it does not make sense to include the lagged values of yt in the zt equation, since it does not help you to actually forecast or predict zt better. Okay, so this is what we are doing in the grandeur causality test. Thus, if yt does not improve the forecasting performance of zt, then yt does not grandeur cause zt. Okay? So you'll be checking for the statistical significance of the lagged values that are entering a particular equation here. Okay? So if all variables in the VAR are stationary, then the direct way to test grandeur causality is to use a standard F test of the restriction, that the coefficients associated with the lagged values of a particular variable are 0. Okay? So here, since we want to test whether yt grandeur causes zt, we want to test whether the coefficients associated with the lagged values of yt are equal to 0. Okay. So here, this is the general notation for a var model itself. So your var model will again have n variables. Okay, so this is the vector of intercept terms. This will be the coefficients associated with the lagged values. Just think that there could be p lags of each of the variables that are there in your var model, basically. Okay. Just read this part. I won't read it out. It's basically explaining the notation. Okay, let me know if you have any doubts or questions about the notation. Here your xt vector basically has all the time series variables or all your endogenous variables in the model. So it could be yt, zt, wt, any of those variables. All right, and you could have p lags of these variables appearing in the model. Can I move on to the next page?
Ma'am, this grandeur casualty what you mentioned,
Yeah. Yes.
is it possible for two variables to grandeur cause each other?
Yes, it is. Okay, so that's a good question. So it may happen that there's only unidirectional causality. So it could happen that uh, yt grandeur causes zt, but zt does not grandeur cause yt. Okay, that could happen. Otherwise, there could be feedback between these two variables where yt grandeur causes zt and zt also grandeur causes yt. That's also possible. So there could be bidirectional causality also, or there could be no causality. Okay.
This would be linked to the concept of multicollinearity in some way.
Uh, no, not really, except that there's likely to be a problem of multicollinearity in the var model because of the fact that you're including so many lags of the same variable. Otherwise, it's not linked to it. Okay, so one thing that is important to note here is that grandeur causality is different from a test for exogeneity. Okay, for zt to be exogenous, it should not be affected by the contemporaneous value of yt. So when we have uh, been discussing the var model, the way we have set up our var model, once we've put it in the recursive form and restricted b to 1 to equal 0, you'll find that yt does not contemporaneously affect zt. Okay, so in that case, zt becomes exogenous, which I had mentioned, I think, earlier in today's class. Okay, so for zt to be exogenous, it should not be affected by the contemporaneous value of yt. Okay, but grandeur causality is different because here we are interested in whether the lagged values of yt are affecting zt, and can we better predict zt with the help of the lagged values of yt. Okay, so that's what is stated in the next line if you read it. Then the multivariate generalization of the grandeur causality test is described here below. Okay, so if you have a model with three variables, wt, yt, and zt, okay, if we want to determine whether wt grandeur causes any of the other variables in the system, then you can do it this way. Okay, so estimate yt and zt equations. You can estimate all three also, but just for simplicity's sake, we've taken up the first two equations. Okay, so here estimate yt and zt equations using lagged values of all the three variables. Then calculate the variance covariance matrix of this unrestricted model. Okay, U denotes the unrestricted model. since you're not restricting any of the lagged values to equal 0, that's why it's an unrestricted model. Okay. Now re-estimate these two equations, excluding the lagged value of Wt. Okay, and calculate sigma r. Okay, where sigma is the covariance matrix of the residuals, and r denotes the restricted model now. Okay. So the reason that it's called a restricted model is now we have imposed the restriction that the lagged coefficients associated with the lagged values of Wt are basically equal to 0. That is the restriction we've imposed, and that's why we are excluding these lagged values of Wt from these two equations when we're estimating them. Okay. So after that, in the third step, what we need to do is calculate what is known as the likelihood ratio statistic. Okay. So for this statistic, you need T, which is the number of usable observations. This is, of course, once you've taken lags and differences, since your variables need to be in the stationary form, okay, you might need to difference your variables. So that's why we are saying number of usable observations is equal to T. Okay. Excuse me. Then C is the number of parameters estimated in each equation of the unrestricted system. Okay. So in each equation, how many parameters are there in the unrestricted system that we have estimated in the first step. Okay. Then this will be available to us from step 1 and step 2. Okay. So once you calculate this likelihood ratio statistic, this statistic has a chi-square distribution with degrees of freedom equal to the number of restrictions in the system. Okay. So can anyone tell me how many restrictions are there in this system?
Two, ma'am.
Sorry.
Two, ma'am. Two restrictions for three variables.
Why are you saying two restrictions? You're partially correct, but can you
Ma'am,
tell
two restrictions in the sense that the first restriction will have two variables being set to 0.
which are those variables?
So, ma'am, for example, uh, the contemporaneous effect of ZT on YT and of WT on YT will be equal to 0, and the contemporaneous effect of WT on ZT will be equal to 0.
No, just a minute here. See here, for now, just take it as the var model in the standard form. Okay, so your YT, these are your equations. I'm just typing it out for you. Here you'll have your intercept, okay, plus, let's say, I'm taking two lags of each variable. I'm just showing you one of the equations, all right? Just give me a minute.
Ma'am, this is already in the standard form, right?
Yeah, this is already in the standard form. There are no
So,
contemporaneous variables on the right hand
so
side.
ma'am, what restrictions were you asking about?
Yeah, just give me a minute. So this is your unrestricted model, okay? Since you have included lagged values of WT,
Restrictions
okay?
for the F test, ma'am.
Yeah, just give me a minute. You'll understand once I put in the next part. So what I've typed here, the first equation is your unrestricted model. I'm typing only the first equation from your unrestricted model. Now in the second one, this is your restricted model. Okay, here I am excluding this part. Okay. Can you all see it now? Okay, so now based on these equations, again similarly you will have one more equation for zt. Okay, so in the first equation again you will have all these terms. It will be 2 1. Okay, this will be 2 1, this will be 2 2. Okay, the coefficient subscripts will change, but basically the structure is the same. So you'll have one more equation for zt. So you've estimated these two equations this way. Just give me a moment. So this will be your unrestricted model, two equations, one for yt, one for zt, which has lagged values of wt. Now in your restricted model, again you're estimating two equations, one for yt, one for zt, but this time it is excluding the lagged values of wt. Yes, Rashi, you wanted to answer?
Ma'am,
Yeah.
now, actually I do agree with Govind's answer, what he initially said,
Hmm.
because as per the very first equation that we read in this whole the structural var, it was according to those equations it should be two only, and the ones that you wrote, I understand them, but it depends upon the lags you have taken. So, for example, if we increase the lags, so then the number of restrictions will also increase subsequently. But according to the structural var equations, I think it should be two only, if I'm understanding what Govind tried to say.
See, both of you are partially correct. Okay, but let me just put in the next part of it. It'll just take a minute, so I'll quickly do it. Okay, now this is again from your unrestricted model. Okay, and this is from your restricted model. Both of you are partially correct. I don't disagree with you on that. Okay, so these are your two restricted equations, this and sorry, unrestricted equations, which have the lagged values of wt, this and this one. Now these are your restricted equations. Okay, you've estimated both this and this. So now how many restrictions are there? Here you've excluded two wt terms, the first lag and the second lag. Again here you've excluded two wt terms, the first lag and the second lag. So your total restrictions are actually 4. Is that clear to you all?
Yes, ma'am. Got it.
Okay.
So basically, we are talking about the restrictions for danger causality or the
Yeah.
exogeneity test.
Yes.
Yes, ma'am.
Yeah. Okay. So here, let me just come back to that. So actually, there are two P restrictions. Since there are P lags in each of the equations, and you have estimated two equations, that's why there will be two P restrictions. Okay. So in our case, it is 4 restrictions. Then here, what is C? Okay, this is also important. Here C is not the total number of parameters in your var model or in your system of equations. Okay, instead it is the number of parameters estimated in each equation of the unrestricted system. Okay, so each equation will have the same number of parameters, so you can pick up any one of the equations and check how many parameters are there in one of the equations. Okay, not all the 3 equations or the 2 equations that we've estimated here. So here in this case, C will be equal to 3p plus 1. Since each variable has 2 lag terms, so it will be 3 into 2 plus 1. Okay, because the unrestricted yt and zt equations contained lags of yt, zt and wt plus a constant. Okay, so because of that, there will be 3 into 2 plus 1, okay, that is 7 is the value of C here. Okay, so that's how you'll be able to calculate the likelihood ratio statistic. Now, if you find that the value of the statistic is greater than the critical value, you will reject the null that there is no grandeur causality. Okay, so the null is that there is no grandeur causality. The alternative is that WT grandeur causes YT and ZT. I hope this is clear to you all how to conduct the test itself. If you have any doubts or questions, please let me know. Okay, so this is the part that I was talking about when I think Mr. Ram Gopal was asking his question. So I said this part might actually explain it. So one example for grandeur causality, this is quite a famous example. So here, this particular VAR equation, okay, one particular equation was taken from a VAR model, and this is quite a famous empirical study. So here we are looking at certain variables. Okay. YT denotes GDP. So this is nominal GDP. This is nominal money supply. Okay. Then this is government expenditure basically, and this is the lagged value of nominal GDP again. Okay. Now, Friedman and another person, I think Kuttner, okay, used several measures of money supply here. That is the money base or your monetary base, then M1, M2, and various short-term interest rates to capture or as a proxy for this money supply variable. Okay, and they estimated a 3-variable VAR over different sample periods. Okay, so basically, when they were checking for grandeur causality, okay, what they were interested in finding out is whether lagged values of money supply can actually help us forecast nominal GDP better. Okay, because there was a widespread belief that money supply affects GDP with a lag, and we can actually forecast or predict future values of GDP better if we know the past values of money supply, or on the basis of past values of money supply, we can actually predict future values of changes in GDP here. Okay. So this is the structure which they used, and we are looking at one particular equation. The other equations would have obviously had money supply as the dependent variable, then government expenditure as a dependent variable, and so on. Okay. So this is a 3-variable VAR. So what they found is when they conducted the grandeur causality test to check if these lagged values of money supply should be entering this GDP equation. This is the change in GDP. Okay. And this is the change in money supply, since delta is appearing here on both sides. So they were actually testing to see whether these lagged values of money supply, changes in money supply, should be appearing in the GDP equation. Okay. So they had, or they found something very interesting, that if they took the time period 1960 quarter 2 to 1979 quarter 2, they found that money grandeur causes changes in nominal GDP. Okay. So if we know the lagged values of changes in money supply, it can actually help us forecast changes in GDP better. That's what they found. Whereas over the time period 1970 to 1990, okay, they found that money does not grandeur cause changes in nominal GDP. So somehow the relationship between money supply and GDP had broken down, and we could no longer forecast future values of changes in GDP based on past values of money supply changes. Okay. So this is what they found on the basis of their econometric work. Any doubts or questions? So this might answer some part of the question, okay, which Mr. Ram Gopal had asked earlier. It has probably been become increasingly difficult to actually maybe affect GDP through changes in money supply. Okay, and you'll find that even the monetary transmission mechanism, if the RBI or any central bank announces a change in interest rates, for example, if they decrease interest rates today, the impact will be felt only with a lag. We do not see an instantaneous impact of this change reflected on other macroeconomic variables like GDP. Instead, the impact will be felt over several quarters, and it usually takes a very long time for the impact of this full, how much the interest rate has been decreased, for the full impact of that to be felt, it will take a very long period of time, sometimes several quarters and years go by before the full impact is experienced. So that might be one reason. What could be other reasons? Can you all guess? Take a guess, hypothesize and guess. What happened around this time, 1979? This is quite famous, so you all might be able to guess what had happened.
The oil shock around this time. So
Yes.
inflation. So that might have weakened money's power to impact GDP.
Yeah. Okay. So oil prices shot up because of uh, the oil price shocks around that time. Okay. The OPEC countries had actually started restricting the supply of oil and so on, because of which oil prices shot up. So that was an important event, and then we saw stagflation, we saw recession in the US and so on. So there were several things which happened around this time, because of which the relationship between money supply and GDP sort of broke down during this time. Okay. And you'll also find that later on there were several financial innovations. Okay. So a lot of money goes into other financial instruments and so on. So there's been a lot of financial deregulation. Okay, so because of this, it might not affect GDP directly. Okay, uh, so that could be another factor because of new financial instruments emerging and so on. So that might have led to some sort of a breakdown in the relationship between money supply and GDP. Even today, if you try and look at various studies, you'll find that although the government and many central banks are doing a lot of things in terms of monetary policy, the impact is often felt very, very slowly. Even after the financial crisis of 2008, 2009, you'll find that interest rates were brought down to almost zero and so on, but still economies took a very long time to recover. Okay, some have not even fully recovered yet, and you still have them actually deciding whether to stop the whole bond purchase program and so on, quantitative easing. Okay, so all these factors are there, because of which the relationship between these two variables might have broken down.
Ma'am,
Yes.
isn't this in a sense the Lucas critique? What Robert Lucas was trying to say?
Uh, yeah, it is possible that we can apply the Lucas critique here, that by the time we actually implement policies and so on, that the actual behavioral relationship has changed, or the coefficient parameter values have actually changed in that duration of time. Okay? So before the impact of those policies is actually felt. So yes, okay? So many people might attribute it to the Lucas critique also. So I think for today we'll stop here, because the next part is related to a different topic. Let me just check. I think it's co-integration. Yeah, we'll be starting with co-integration next. So we'll stop here for today before I get into that. Any doubts or questions regarding whatever we've studied so far for VAR models, grandeur causality? Okay, so one thing is, if you take this same equation here, you could also have a second equation where you have money supply, and you have on the left hand side and GDP on the right hand side. And then you can check if GDP grandeur causes money supply. Okay? Or does do past values of GDP actually help us to predict future values of the money supply? And then you can see what is the result from your grandeur causality test. Okay, so these sort of things are usually done. So you'll have multiple equations like this, especially after estimating VAR models, usually a grandeur causality test is conducted. Okay, so these are,
Uh, Ma'am, one academic question.
yes.
This particular equation of Friedman, is it the GDP is a nominal, or this will be in real terms, I guess?
No, actually in this case it is changes in nominal GDP. So
Oh,
uh, even I'm not sure why nominal GDP was taken. Okay, perhaps if both variables are nominal, then it does not really matter. Plus, you're taking differences. Okay, so that might actually
I thought usually money supply is taken as money supply in nominal terms, and GDP is usually taken in real terms, so that the inflation effect is already built in the price effect. Or you look at prices separately, introduce a inflation level in the equation.
generally it is recommended that we use real variables itself, but often in the case of money supply, what is done is that money supply is taken in nominal terms and then a price variable is included on the right hand side. Or if, for example, if money supply is coming here, so we would have real money supply, which is m by p. So once you take logarithms, for example, these are logarithmic changes. So once you take logarithms, it will become ln m minus ln p. So we shift p this side, so it becomes plus ln p on the right hand side. And so that takes care of the fact that on this side you have your nominal money supply now, but here you have the price variable. So usually something like that is done. I'll try and trace this paper and see why exactly they've taken nominal GDP and nominal money supply changes again. Okay, so this part I'll clarify in the next class, but usually we use real variables. All right, so any doubts or questions related to what was taught in today's class? Okay, nobody seems to have any doubt. So I'll share the notes by tonight. And the other thing, I'll just continue with my feedback for your assignments. So again, I will stop recording for a moment. Yeah, for probably the next 5 minutes, I'll stop recording.